Hello, and welcome to this new series of videos, a course on developing mathematical proofs with the Lean Proof Assistant. Now, it's worth really being clear up front that this course is not going to be advanced. It's not going to be encyclopedic in terms of covering everything you can do with Lean or every kind of mathematical proof. The real reason for creating this course is to help others like myself who are interested, have an enthusiasm for mathematics and computer science, but couldn't get past all the tutorials and courses that are out there. So the idea is to kind of make this course as gentle and as easy as possible. Starting small, developing small proofs, slowly, step by step, seeing the kinds of things you can do with a Lean theorem prover, and developing our confidence in that way, so that by the end of this course we have some experience and some confidence that we can go on to learn more interesting or more advanced things. So the idea is to get us from 0 up to maybe about, say, 2030, so that we're ready then to kind of continue to do more if we want to. And then the next tutorial we'll actually get hands on. So what is a proof? Well, let's start with mathematics. So for thousands of years, humans have been using their kind of brain power, and some might say we have more brain power than needed to survive, I don't know. So we've been using perhaps some of the extra brain power to think about mathematics and interesting abstract ideas and concepts, and then wondering whether some ideas are true or not. And the thing with mathematics, and that's different to science and engineering, is that we determine truth through a logical argument, so that there's no doubt by the end of a logical argument that something is true or false. Whereas in science and engineering, we do experiments, we develop a body of evidence that something is likely to be true, and that's perfectly valid and normal in science, but it's not actually valid in mathematics. So there may be lots of evidence for an idea, a proposal, a conjecture in mathematics, but there might just be one counterexample, which means that it isn't always true. So in mathematics we don't do it that way. We have to have a rigorous, solid, watertight, airtight process for determining if something is true. And just to pick some interesting examples from our thousands of years of history of mathematical truths. So some mathematical truths are not interesting. Maybe they are to some people. Some are really interesting, and they are very applicable as well, and some aren't, but that doesn't matter, because mathematicians quite often are interested in interesting ideas because they're interesting, not because they're applicable. So just looking at some of these three. So the first one was the idea was that the primes are endless. So as you know, primes are those numbers on the number line which can't be divided into smaller components. So let's say 6, that is 3 times 2, so that's not a prime. 7, something times something isn't 7. We don't think of 1 and the number itself. So even though 7 is 7 times 1, that doesn't count. You might have 8 here, and that's 4 times 2, so that's not a prime. This one is. 9, that's 3 times 3, so that's not a prime. 5, that's a prime. So the idea is that the question is, do these kind of go on forever? Are they endless? And you can sort of maybe think that if I've got a very large number, big number, maybe there's lots of opportunities for smaller numbers to multiply up to that number. So maybe they become rarer and eventually run out. And that's a really good question. Do they run out? Is there a last prime after which all the numbers have factors? And some people in history might have thought yes, they do run out, and others might have thought no, they never run out. And you can't sort of say yep, they definitely run out, and I say so because I'm a bigwig and I'm really important and you have to believe me. No, you have to prove it mathematically. And once you've done that, then as long as the argument is solid, you can't argue against the conclusion. And as you probably know, the number of primes is infinite; it doesn't run out. The next one, another interesting idea from history, is the irrationality of square root of 2. So in the old days, the ancient Greeks saw the world as being very much sort of centered around whole numbers and ratios of whole numbers. They thought that was a very central and important idea, that everything in the universe could be measured and created and kind of constructed from whole numbers, combinations of whole numbers, ratios of whole numbers. So if we take a square with sides 1, then this distance, the diagonal, is the square root of 2. It's 1 squared plus 1 squared and then square rooted. And this thing is actually irrational. It can't be expressed as a ratio of 2 whole numbers. Now, that would have blown up the worldview of the ancient Greeks, and it did. I think somebody suffered quite a lot for that. I'd have to look up the history, but I think somebody might have even been murdered for it. So being able to prove that this quantity, square root of 2, cannot ever be expressed as a ratio of 2 whole numbers, it's irrational. That's an interesting thing to be able to do. It's an important thing to be able to do. But again, at that time, there's a lot of heated argument and firm beliefs that everything could be expressed as a ratio of whole numbers. Everything was rational. So somebody coming along and saying, nope, there's a number here, there's a quantity in real life I can draw or paint or kind of have a field of grass with side 1, and then square root of 2 as the diagonal, and that thing that's in real life can't be expressed as a ratio of whole numbers. That would have blown up that worldview. So you have to be really convincing in your argument that was true, and that did happen. The proof's quite interesting, actually. It's worth having a look. Maybe we'll do it, I don't know, in this course with the Lean proof assistant. Another interesting one, which is a little bit more abstract, is the 4-color theorem. So the idea is that if you've got a map, a geographical map rather than a mathematical map, of say kind of countries that are connected and have borders, and some don't and some do, and the idea is, what's the minimum number of colors paint ink that you need to color the map so that 2 countries that touch each other, that share a border, are never they're not the same color, so that you don't get kind of confused. That's an interesting question, and it turns out the magic number is 4, the 4-color theorem. So you don't need more than 4 to color any map. And the proof of that was not actually that long ago. It was in the 1980s, I think. So after thousands of years of mathematical history, we only managed to do that in our recent decades. So that's quite an interesting one. You might have seen in the news in the recent years about Fermat's last theorem, which just stood as an unsolved problem, was eventually proved by Andrew Wiles, and that was a momentous occasion in the history of mathematics. But again, the statement of the problem was simple and nice, but the proof took a long time. In fact, let's it's worth kind of just looking at that. So the idea of Fermat's last theorem was that if you take an expression like a to the n, b to the n equals c to the n, can we satisfy this? Can we have combinations of a, b, and c and n which are whole numbers? And does that work for any n? So for the simple one, n is 2. We know that we've got the Pythagorean triples. So you might have 3 squared plus 4 squared equals 5 squared, and so that works. We have solutions to this with n equals 2. But then the idea is, could we have that for n equals 3, 4, 5, 6, and so on? And we couldn't find any. So the idea was that it's not possible at all. A firm statement, any more than 2, n is 2, it's just not possible. And that's quite a bold thing to say. And Fermat said he had a proof. Famously, he kind of wrote in the margin, I've got a proof, but I haven't got space to explain it. It's easy. But for hundreds of years, we couldn't find a proof until Andrew Wiles did find a proof, quite a long one. But it was definitely, initially I think there was a little fault in it, but it was corrected. And then that proof meant that we now accept that this Fermat's last theorem is true. So that's another one where, just because there was lots of experimental evidence that it was true doesn't mean it was true. We only say it's true once we have a proof. So just to summarize that, truth is not determined by the weight of experimental evidence, and that's really important. That's why we write proofs, and that's why we're here, perhaps learning about the Lean proof assistant. So what is a proof? Well, it's a logical argument, and it's designed so that anyone reading a proof or listening to a proof can't argue with the conclusion if all the logical steps in the proof are correct, and that's the value of a proof. So we want to prove something, an objective, and to get to that objective, we start somewhere that's kind of familiar and smaller in terms of scope, and we say, we start at these agreed positions, statements that we kind of assume to be true or know to be true, and then we make logical arguments to develop a new statement, and then we progress the argument and we do it again. So in logical steps we get to the objective, and once we've done that, we have a proof. And the reason we can say a proof is a good way of doing this is that as long as each logical step on that journey to the objective is valid and correct, and we can examine it because we can read the proof, then the conclusion is true. Now, where we start is an interesting question. So everyday proofs, things we might do at school, things we do when we're kind of doing maths exercises, we often start with commonly understood statements that we kind of know are true. I'll give you an example. So we know that if we've got a real number like 3 minus 3 minus 20 54, if we square it, it's always positive, and that's kind of well known, and for us, and it's safe enough for us to say, yep, that's fine, and we can use that as one of the kind of platforms on which to build a proof. So the square of a real number is always positive, 0 or more, and it's absolutely correct. You might challenge that and say, well, how do we know that? Why do we all kind of assume that's true? Why is that a part of the kind of body of knowledge that we all kind of agree is true? We've just been saying for the last few minutes that everything has to be proved, and it's true, everything has to be proved. So you may be aware that actually there are things called axioms, which are the bottom level of this structure. So the axioms are things that we accept are true, because we have to start somewhere. We don't challenge them. Well, we can, we just end up with a different set of axioms. So the axioms are the foundation and the things that we all agree, and then we build up mathematics from those axioms using logical steps. Now you can imagine those axioms are really quite low level, fundamental. So saying something like the square of a real number is positive, that's not an axiom, it's not fundamental enough. So to give you a flavour of axioms, you can look online to find common axioms that are in different parts of mathematics. So numbers that we all kind of familiar with, the natural numbers are probably the simplest set of numbers, and we have to think about, well, what are the axioms? How do we define those things and how they behave? What's the minimum set of the most fundamental things that we have to agree on? And you can look them up. They're called the piano axioms. I think there's about 5 of them. And one of them is that if n is a natural number then its successor is a natural number. So that's not about multiplication, it's not about division. Those are higher up in that hierarchy. But this is one of the, this idea of a successor is that fundamental enough to be an axiom. Another one is that 0 is a natural number. Now I know that some people start at 1, that's fine. So that's an interesting. So you can look at the piano axioms to get a feel for how simple and low level you have to be an axiom, and on those axioms we then build things like addition, ideas like greater than or less than, and maybe other things. You might build the rational numbers on top of them, but those are further up the hierarchy. Now that hierarchy collapses if we made a mistake along that kind of building, and that's why proofs are really important to check and so on, and that's what the Lean prover will help us do. Another set of axioms you might want to have a look online for are the axioms for set theories. So sets again are very fundamental, basic things, and defining the minimum set of things we have to believe are true about sets. That's quite an interesting thing to think about. As it happens, there is a slight divergence in what people think should be the minimum set. So we've got the Zermelo-Frenkel axioms, ZF, as a very commonly agreed set of axioms for set theory, but then some people extend that with ZFC with another axiom to be able to do more things. So you can see even around axioms there is an interesting possible debate around them. And if that's your interest, that's fantastic. I think it's really good to think about the real fundamentals of the mathematical objects that we kind of work with. So when you think about more advanced concepts like derivatives and integrals, those are way high up on the on that hierarchy of things that we build on increasingly more fundamental objects. So there's the axioms. So that gives us the platform at the bottom. But moving up, we have to say that if we're here and we move up to this step, that's got to be watertight. So that means the logical step also, we have to trust that it's something we can believe the conclusion of. So if I start with some axioms, or even start here and then move on to the next step, how do I believe that next step is correct? Well, I look at how we got there, and that logical step has to be convincing. So we also, through history, have had to develop a framework of logic that we can all kind of believe in. Now you might say, again, we can challenge that, and yes, you can have different kinds of logic, but generally we kind of have enough of a common agreed set of logic to be able to do interesting mathematics. But there's no prohibition at all about different kinds of logic. If your logic is inconsistent, then the results aren't actually that interesting. There's nothing stopping you from playing. But yeah, generally, if your logical framework is consistent, then the results you get will probably be interesting. I just need an example of what we mean by logic. If we say that A implies B, you probably know or have heard that that's not the same as B implying A. Let me think of an example. If it's been raining, that's A, then the floor is wet, that's B. So if it's raining, the floor is wet, A implies B. But if the floor is wet, does that mean it's been raining? Well, not necessarily. I might have spilt water from a glass. So you can see that they're not necessarily equivalent. They could be, but they're not necessarily equivalent. So it's this kind of thing we have to think quite carefully about when we use logic to get from one step to the next in our proof, in our proofs. So those are the two ingredients of a proof: the axioms, which are right at the bottom. And I say we don't, everyday mathematics, we don't have to go all the way back to the axioms. We work with commonly agreed standard results, and then a framework of logic to progress the argument. So what does a proof assistant do? Well, you might imagine, as I did, that software exists, and some software does exist, for automatically coming up with proofs. And as you can imagine, proofs can be quite difficult to invent, to create. Some are straightforward, some require a little bit of inspiration, some have come out of the wild and are really crazy but still valid. So writing proofs is not an easy thing to do, and coming up with proofs that no one else has come up with is really an achievement if you can do that. So there is certainly a lot of research in creating software that can be creative, can automate the creative process. Kind of the AI approaches for kind of generating interesting content. That's an approach. That's something that there's active research around. But that's not what a proof assistant does in the sense that we're going to be exploring. So it's not a proof creator, it's a proof assistant. And what a proof assistant does is it checks the proofs that we write. So we still have to write the proofs, and you might think, well, what's the point of that? Well, you can imagine that we humans, we get tired, we get bored, we make mistakes, we have gaps in our knowledge and understanding, so we can make errors as we write or check proofs. So if a computer can check a proof, then that's really valuable. So it kind of democratizes that process a little bit. It means that there's additional assurance that if a computer proof assistant says that this proof is correct, then it very, very likely is, unless there's a bug in the proof assistant. It also means that if mere mortals like ourselves invent a proof that's novel or interesting, we don't need necessarily to find time with a senior professor to check that, because if a proof assistant has said it's valid, then we're kind of we can with a lot of assurance say, yep, that definitely is true. So that's what I mean by democratizing the idea of creating and checking proofs. So that's really, really valuable. So that's what Lean does. And if you're interested, do continue with us. In the next few videos we will get hands-on, but in this video we're just kind of talking about the concepts and ideas. So Lean is actually a programming language in the same sense that Python, C, Lisp, Haskell are programming languages. It's a functional programming language. If that means something to you, great. If not, don't worry about it. But one of the libraries that's kind of developed around Lean, Mathlib, has been the center of this huge interest, a recent interest actually, and growing interest in using Lean with Mathlib as a proof assistant. It seems to be a really good combination, and there's been a lot of interest recently with lots of people learning it and getting involved, and some world-class leading mathematicians also starting to get involved and use it and maybe develop it. It's starting to become part of undergraduate mathematics courses to learn how to write and check proofs with Lean. So if you join us, then we're part of a really interesting wave. A lot of people will be using Microsoft Visual Studio Code with the Lean extension. That's partly because the person who created this proof assistant actually worked at Microsoft, so naturally they would want to have that system work with Visual Studio Code. If you can use it, I think you should. It's available for Windows, Mac, Linux, and the Studio Code is free to download. The Lean system, I think, is fully open source, and it just makes it easy. Normally when people say, oh, it's easy, you often have some complicated setups to do, but actually I was surprised that you don't. You just install the extension and it just all works. It creates a runtime and so on by itself, which is really nice. It's quite smooth, and it's also a richer environment where it provides feedback and kind of helps you with bugs. So if you can do that, that's great, but you don't have to. So if you don't want to install anything, and you can't, then you can use a purely web version where you just use a website through your browser, and that works as well. And everything in this course will be tested to make sure that it does work on that website as well. So that website is this one, live.lean-lang.org, and let's have a quick look at it. So this is the website, and it's new and it's still developing. So there's still some things that they need to kind of work out. One of them is that I think through a period of inactivity, the backend server stops, so you just need to restart it. And this is evaluating 3 plus 4, and it's telling us it's 7. Let's change that to prove that it's doing something real. Let's say 3 plus 17, and it's 20. Now you notice I didn't press enter or run. That's because the way Lean works is it's constantly checking the proof as you write it and providing feedback on it. So you never really click run. It's continuously evaluating and running. I hope you can see that. I'll make the text a little bit bigger. So let's try another one. 22 plus 19, and that should be 41. If I don't complete that, then it's kind of telling me that I haven't finished. There's a bug and error over there, and we'll learn more about that as we go. So this website online is a possibility if you don't want to install anything, or you can use the Microsoft Visual Studio Code, free to download. And let's also have a quick look at that as well. So this is Visual Studio Code, and here is a program that we'll be looking at next time. And as you can see, if I kind of hover over things, it tells me about them. On the right hand side, there's some errors. Won't worry about it today, but it can do interesting things. Like if I click somewhere, it tells me what part of that mathematical proof is being worked on. So it's kind of a rich environment, so you may prefer that. Color kind of annotated, so you can see the keywords are in different colors and so on. So it's potentially a nicer environment to work in. Great, so we'll stop there. So today we kind of just introduced or reminded ourselves what a proof is and why it's important, and the kind of the general idea of using axioms and then commonly known truths potentially to start from, and then using a framework of logic to reach a conclusion. Next time we'll actually start by looking at a real simple proof and looking at some code to kind of implement that proof and check it's true. So looking forward to that. See you next time. Bye.